Imagine a world where anyone could create a convincing fake face or video of someone else with just a few clicks. Unfortunately, we are already there. Deepfakes and synthetic faces, like those generated by StyleGAN, are increasingly common and pose serious challenges to society. In our project Deep Learning-Based Detection of Synthetic Face Images, we will today present to you the following parts: introduction, dataset, model architecture, training process, results, and conclusion. Deepfakes have legitimate applications in entertainment and media, but they also have a darker side. They are used to spread misinformation, conduct fraud, and compromise cybersecurity. Platforms like "this person does not exist" demonstrate just how easy it is to generate hyper-realistic fake faces, which makes it harder to trust digital content we consume daily. To address this issue, we present a deep learning approach to identify synthetic faces with high accuracy. This model is trained on a dataset of real, StyleGAN, and Stable Diffusion generated images and is designed to distinguish between authentic and fake images effectively. Our objective is to present robust detection methods to accurately identify synthetic faces. By doing so, we aim to contribute to the fight against the misuse of deepfakes in critical areas like social media, law enforcement, and cybersecurity. Why does it matter? Ensuring the authenticity of digital media is essential for trust in today's digital age. Robust detection tools can protect social media users from deception and provide valuable resources for law enforcement to counteract altered content. In the next part, we will present a use dataset for you.
This topic requires a comprehensive dataset for synthetic face detection. It consists of over 232,000 images from both real and AI-generated sources, which are needed to achieve optimal model training. In the following slides, I will break down the composition of the dataset and explain how it was utilized for training the deep learning model. For the real human face images, two significant datasets were included. The first dataset contains 30,000 high-quality celebrity face images and was originally created by NVIDIA for their generative adversarial networks research. The second dataset was sourced from Flickr and contains 95,000 diverse face photographs featuring a wide range of ages, ethnicities, accessories, and backgrounds. Let's move on to the first synthetic face dataset. Here, 39,500 images generated using the StyleGAN technology were included. StyleGAN is one of the most advanced generative adversarial networks for creating photorealistic human faces, making them particularly hard to detect. StyleGAN was developed by NVIDIA researchers in 2018 and is a groundbreaking generative adversarial network architecture that revolutionized synthetic image generation. It introduced a novel, style-based generator approach that allows unprecedented control in creating highly realistic artificial images. Next, the dataset also includes 11,536 synthetic faces generated using various versions of Stable Diffusion, a powerful text-to-image AI generation model, which I am sure most of you are familiar with. The versions included here are Stable Diffusion 1.4, 1.5, 2.1, as well as the latest SDXL 1.0. By using faces from multiple versions of Stable Diffusion, the model can learn to detect synthetic faces across different generations and quality levels. EG3D, introduced by NVIDIA researchers in 2022, represents a significant advancement in 3D-aware image synthesis. It combines efficient neural rendering with geometric control to generate highly photorealistic faces with precise 3D consistency. This architecture innovates by incorporating 3D geometry into the generation process, allowing for multi-view consistent image synthesis and enhanced control over facial features or poses. Finally, the dataset also includes 21,256 synthetic face images generated with SFHQ2, which represents a unique hybrid approach to face generation. What makes this subset particularly interesting is its sophisticated pipeline that combines three different technologies: 3D modeling, Stable Diffusion 1.4, as well as StyleGAN 2. Let's break down the final composition of the complete dataset. There's a relatively balanced distribution between the real and synthetic images. The real images represent 54% of the total dataset, while the synthetic images make up 46% of the total dataset. For model training, the total dataset was split into three sets: 70% for training, 20% for validation, and 10% for testing, thus using a standard 70-20-10 distribution to ensure robust model training and evaluation.
The model we used is based on DenseNet 1-to-1, a state-of-the-art convolutional neural network known for its densely connected layers. The architecture includes base model uses the pre-trained DenseNet 1-to-1 for feature extraction, leveraging its efficient feature reuse and gradient propagation. Custom layers are a global average pooling layer followed by a fully connected dense layers, outlayers for regularization to reduce overfitting. The output layer shows a single dense layer with a sigmoid activation function enabling binary classification to differentiate between real and fake images. Why this architecture? DenseNet 1-to-1 is known for its ability to reuse learned features through its dense connectivity pattern. It's particularly suitable for tasks that require detecting subtle distinctions such as real versus fake face detection.
And processed, how training parameters were configured, and how the model's training progress was monitored to achieve optimal face detection results. In the pre-processing phase, data consistency was ensured through three key steps. All images were resized to 260 by 260 pixels for stabilization. Pixel normalization was applied, scaling values between 0 and 1 to improve training stability. Lastly, data augmentation was implemented using image data generator to reduce overfitting. The training configuration was optimized for efficient learning. Images were processed in batches of 100 and the Atom optimizer was utilized for dynamic learning rate adjustment. Furthermore, the binary cross-entropy loss function was chosen for the classification task. To maintain model quality, early stopping was implemented, which saved the best weights through model checkpointing. Throughout training, key performance metrics were closely monitored. The model's progress was tracked through accuracy and loss measurements for both training and validation sets. The 1000 steps per epoch were continuously monitored for processing time and batch completion to ensure smooth training progression.
The final model achieved an accuracy of around 97% on the test set, demonstrating its effectiveness in detecting synthetic faces. The F1 score further validated the model's balance, performance, and precision and recall. Here you can see some results of images input for testing purposes. The accuracy is between 99 and 100%. Our analysis revealed that the model performed consistently across different lighting conditions and facial expressions, highlighting its robustness.
This project demonstrated the effectiveness of using deep learning in detecting synthetic face images. Through careful dataset composition and optimized training configurations, the model learned to distinguish between real and synthetic faces. And while the results show promise, the rapidly evolving nature of AI face generation technology means that detection methods must also further continue to adapt.